before we start, let me make a quick recap on what distributed systems are, so we are all on the same page. Distributed systems. A distributed system is a collection of independent components that, from user perspective, act as a single current system. Right? Does that make sense? They have three main characteristics. They have many, but the main characteristics are that they have concurrency. Concurrency is about dealing with many things at once. Then they have a lack of global clock notion, because different services can operate in different hosts, and they don't share a clock notion. Each has its own one, maybe synchronized with MTP or something like that, but it has its own one. And the last one, but not the least important, is that they have independent failures. And failures can come from three different sources. The first one could be faults in the network. If you read this book from Sam Newman about building microservices, he states that network can fail and will fail, and that's true. Network can fail in many ways. Then we have failures in hosts, because as we said, services run on host, and the host is a problem itself, is a system itself with its own problems and errors. So let's say you have a service running in a host, and then the host ends up with a full disk or a corruption in the disk, then the service might not be able to operate, right? So, but that's not part of the service failure, it's mostly part of the host failure. And then we have independent component failures. And that could be because you have an unhandled exception, a fatal error, these kind of errors that are proper or related to the application itself. So yeah, they can fail also independently. For example, if your service cannot connect to a crucial dependency, if there is a new pointer somewhere, all this stuff can trigger a component failure. As what is important about this is that, as we stated, we have three different sources of failure. So as you can see, there are many ways your system can fail in. So you better make them fail gracefully, right? So now that we're talking about this, I would like you to spend a couple of seconds to think about the system you are familiar with or you work with on your daily basis, right? So we all have one in mind when I do the examples, right? Okay. I want to introduce a distributed system you might be all familiar with. So we talk about the same thing, which is this one. As you can say, this is independent component that from user perspective is one single current thing, right? This distributed system has one specific use case, which is the tap. A person opens the tap, water flows out, person closes the tap. Pretty simple, right? But this has its own problems, right? Let's say we have a leak in one of the pipes. Well, that leak will have an impact in the pressure of the water. So from this person's perspective, due to a lowering in the pressure, the water will flow slowlier, and eventually the water will flow through the tap, but the person will perceive that it was slower than usual, right? But they will be happy in the end, right? But let's go deeper. Let's say we have a huge blocker in one of the pipes, right? Which is causing that the water cannot flow through the pipe, and this person cannot see any water at all, right? So this person might think, okay, there might be some delay in the water because of pressure or this stuff, and we'll wait and wait and wait up to the point they will realize that water is not flowing, right? What is interesting about this is that this person will perceive that there is something wrong in one of the pipes or maybe in one of the components of the piping system, but they might not be able to pinpoint where the problem comes from, right? Maybe they can look for wet walls, looking for some leak somehow, but no more than that, right? And
I don't know about you, but this situation looked very familiar to me, right? Because I work in an internet company, right? And modern internet services are nowadays implemented as complex large-scale distributed systems, right? So when you had one component in isolation, or sorry, when you had one or two components, it was easy to pinpoint where the problems come from by just looking at them in isolation. But now a user request traverses dozens of services, right? So before you aim to solve the problem, you need to understand what are the interactions. This specific use case is a very simple one. We have an API for media. We have a user or a client doing requests to this media API. In front, we have an API proxy, which checks whether you have access or not to this resource, or whether you are correctly authenticated to hit that resource, right? So we have the API proxy, and then the out service, which is the one that determines whether you can access or not, and then the media API, which will request to the image service and to the video service, right? So let's say we have a latency problem in the image service, right? That latency will be propagated all the way up to the media service and then to the API proxy, and then the user might feel like there was a latency. This request took longer than it is expected. So even for an engineer looking at this overall problem, might know that there is a problem, but not might be able which service is at fault, right? For many reasons. Probably since we are in a distributed systems architecture, we probably have microservices. Microservices not only come with changes in the technical side, but also changes in the cultural mindset, right? So we have more independent teams. We have teams that build, release, and operate their own services. We have ownership. So first of all, an engineer might not be able to know which are the services participating in this use case, right? That's by first. And the second, even if that engineer knows what are the services participated on this, they might not be able to know what happened because it's not an expert on every single service, right? Imagine you have a company with 400 services. Can you point one in your organization which is an expert on the 400 services? Probably not, right? And if you know, please let us know. We are hiring, but probably not. So let's keep this parallel situation with the previous distributed system, so we understand it better. Let's say now we have a bigger error in the authentication service. We have aborting connection error, right? 1,152 error. Well, the out service, given that it cannot connect to its crucial dependency, will have to return a 500 to the API proxy, and then the API proxy will return a 500 to the user. And again, if you aim to fix this problem, you first need to understand what are the components involved. And that's not trivial, right? So, okay, right. So, I think we should go back to the pipe because things were simpler there. So, in my mind, it would be awesome if there were a way that so the error can yell at you, hey, I am here. I am clogging your pipes, right? Come and fix me. Because then, with that information, where it is and what it is, you can just jump in and fix the problem, right? And you might be thinking like, we have something like that in software, right? We have logs. We have evidence of what is happening. We have logs, right? And yes, we do have logs. And we have had logs for 40 years. Problem with logs is that this kind of situation is never like this. It's usually like this, right? Because we have concurrency. We have services and machine might be shared simultaneously by many different clients. So you will have a lot of requests going on at the same time, right? And this kind of situation might end up in this kind of logs, which I keenly colored for you, so you understand which one belongs to which service, but in real life they might not be like that. Because logs represent events in the system, right? There is no scope, there is no context around logs, and I am not even talking about asynchronous operations, right? And you might be thinking, well, in my company, we add the request ID to every log record, and then we can correlate them, and we solve the problem. Well, let's say you are in an on-call duty, it's 3 a.m. in the morning. I don't want you to be correlating this with this because of the date, which one comes first, which one originated which, right? That will be really hard. Because logs will tell you that something happened, but they won't tell you why, no, what was happening at that time when this error happened, right? So, how can my dream become true, right? What could we use to have such a expressive error finding? Well, there is when distributed tracing comes to unclog your pipes. Distributed tracing is a way to understand what happened in your request. It's about tracking and analyzing requests as they bounce around distributed architectures as a whole, right? You can think of it as an action replay for a specific request. I say request, but it could be message-based use cases. In this graph, you can see what happened for the request to the media API, right? You can see that the API proxy requested the out service, then the API proxy requested the media API requested the video service, and then it requested the image service, right? And even you can see the error yelling at you, saying, hey, I am here. It's aborted connection, right? So what is good about this? First of all, this is request scoped. You don't see any noise about concurrency. You just focus on your request. Concurrency is mute. Second of all is that you have causal relationships. You can understand what are the dependencies, what are the interactions between services, and that's good. You can see that this is timelined. You can see how things happened across the time, and can understand latencies, which one took more time, and so on. And finally, you can enrich your data with annotations. For example, in this case, you can see that in the image service, it tried to retrieve resources, but they were not in the cache, so they had to retrieve from origin. And probably that's an intensive operation that caused an aborted connection in the database, right? This is in contrast to traditional monitoring that focuses on each service as an individual. This presents the use case as a whole, with all the participants, right? Because distributed tracing is something like that. It's a story told by many people, right? So, what answers do I get from distributed tracing? Well, first of all, what services are involved for a request, which is important because we now know what are the players in the game. Second, what happened on each service and how it happened. Then, how your services are connected. What are the critical paths? It helps you to understand dependencies. I will talk about critical path in the next slide because it's very important. And who should I page, right? In which service this happened? Should I page this team that is in charge of this service, or is it a database problem, and should I page the ops team, right? This kind of stuff is very valuable when you are in an on-call shift. But don't take me wrong. I am not saying distributed tracing is a silver bullet that will fix all your operational problems for the services, right? Distributed tracing has friends, and they have different characteristics. In this graph made by Peter Burgon, we basically explore all the characteristics of different signal collections. We have logs that I explained it. Logs tell you that an error happened. It's focused on events in the system. Then you have metrics. Metrics tells you how many errors of this type happened in the system. It helps you to understand trends. Whereas tracing tells you what happened and what is the impact of it across your distributed system, right? So let's look at the benefits. Well, it's almost immediate feedback. You can look at the traces right after they happen. It's a request scope and it's actionable because it tells you where the error happened or what was the operation that took longer and caused the latency. It gives you a system insight because it clarifies non-trivial interactions between your systems, right? You can see them graphically as a tree graph. And it gives visibility to critical path and dependencies. Critical path is something that Google, for example, was looking at when they moved it to microservices. Basically, they realized that moving to microservices caused latencies because now services were connected over the network, right? And they were spending effort and resources in improving those services, improving the response times, right? But at some point, they realized that some improvements didn't have any impact on the user-facing response time, right? And then this concept of critical path became crucial because if you, let's say in this graph, you have operation 1 and operation 2 that happen in parallel, and you spend your time improving operation 2 all the time while operation 1 is the one that is causing more latency, then you're wasting your money, right? And that's something that Google found. What is also true is that it's impossible to intuitively determine which service will have more impact on user-facing response time, right? So it's better to have something that shows you which one is the one causing more latency. So that's another benefit from distributed tracing. As I said, it helps you to understand latencies, and it's request scope. But it's not request lifecycle scoped. This means that if you have a request which is synchronous, and that request ends up in some other asynchronous operation, you will be able to see the whole in one trace. You don't have to chase logs, right? Like, okay, in this half an hour, I looked for these logs with this request ID, and then 1 hour after, I will see the other pieces asynchronously. You will see all in one schema. And that's good. So let's look at the trace anatomy now. What is a trace? Well, a trace tells the story of a transaction workflow as it propagates through the distributed system, right? It shows you the execution path, right? A trace is the whole thing related to your request. One request matches to one trace. Then you have a span. Spans are single unit of work. Spans can represent expensive operations. Let's say you have an expensive marshalling, HTTP request, database calls, everything that is error prone, everything that can have latencies, everything that can fail, and everything you want to observe, right? That could be an span. Then you have a context, because as I told you, distributed tracing is one story told by different people, well, but different actors. And for that, you need a context, right? If I tell you about someone and you don't have a context about that someone, then that information is useless. The context can be propagated through HTTP headers. Once you have an HTTP request, you propagate the context in the headers, and then the service receiving it will understand that, okay, I am part of this trace. I will show you that later. Or in the metadata in Kafka messages, for example. So it works for sync and async operations. Then you have tags, which helps you to group spans by a common characteristic. Let's say an SQL statement. Let's say what is the host where this specific operation is happening. And then you have logs. And logs mark meaningful moments in a span's lifetime. Logs are timestamp because they represent something that happened in the span lifetime. And you can have many different logs for the same event in your span. So let's go now for the elements of distributed tracing. This is a very nice analogy built by Nick Munroe from Nike, the shoes company. He explained distributed tracing elements as the three-legged stool analogy. And as every three-legged stool analogy, every leg depends on the other two to work properly, right? As I told you, distributed tracing is one story told by many pairs. So you will see that this is a crucial piece. The context is a crucial piece on how to correlate all these versions of different pairs in one single story. Let's go for the first leg, which is inbound propagation. Inbound propagation is when a service processes a request or consumes a message, let's say. Well, in this case, we have the API proxy that is requesting the media API. And for that, the media API will create an span saying, this is the span I create on behalf of this trace, saying that I received a request, right? And we'll annotate with the get media name too, right? And the second leg is outbound propagation, which is when a service is doing a request to another service, right? So in this case, we have the media API that will request the video service. For that, the media API has to propagate the context, right? Saying, okay, this request is part of this trace. And we'll send it the context, let's say, through the HTTP headers. And then the video service will receive that context and will say, okay, I am creating a new span saying, this is the request that I received from the media API with this information. So all this is collected in one single trace, right? And annotates with the get videos again. And finally, we have the in-process propagation. In-process propagation is local, right? You have the image service, which does operations with its internal dependencies. The database, let's say you have a Redis cache, and then this image service will say, okay, I create this span because I did this query to the database, or I will create this span because I did this on marshalling that was expensive, right? And all these spans that has been reported by different pairs will end up in this trace. And then you will see the full picture. You will see what every service did, right? So you might be thinking, this is too good for being real, right? Do you have any overhead? Does this cause any overhead, either in operating the service or in building the service? Well, that's a valid question. Of course, there are overhead on adding observability in general, right? For users, well, observability tools are meant to be unintrusive. They are not supposed to modify what happened in the system. So from user perspective, having observability or not having it should feel the same. If I do a request to a service, if that service has distributed tracing instrumentation or not, it should be the same for me. I should receive either the same response, either the same errors when it's time for an error, right? They are meant to be intrusive. If there is an error in the instrumentation, it should never be propagated up in the stack so the user can perceive it. Of course, it adds some small latency because it will allocate more memory for the spans that I show you. But as I said, they are meant to be unintrusive and they are optimized for that, right? They try to spend the less or allocate the less memory possible and to have the less impact. Then you have also the sampling. Sampling is something that Google came up with when they started doing their distributed tracing tools. Sampling is about only looking at a sample of all the requests, because that's all I need for understanding what is happening. And that makes sense. If you have a high traffic system, you don't need to store every single operation to understand what happens or to detect errors. You just need a sample, right? Let's say 1%, 0.1% if you have really high traffic. And that also reduces the overhead, because now that you are not sampling some of the requests, then that allocation of memory is not happening, right? That reduces overhead. And finally, don't trace every single operation, because you should only trace those operations you are looking at after, right? Only those that are error-prone, only those that can have latency. You don't have to trace everything, because then you will have a huge trace that you won't understand. You only need to focus on what matters. And that's for users. For developers, there are also overhead, because now you have to build code that can be observed. The main challenge is that not all libraries are ready to plug instrumentation. I keep saying instrumentation. Instrumentation is the action of plugging instruments into your code to report signals. Let's say metrics, logs, all these signals. And there are instrumentation for most of libraries. If you work in Go, there are instrumentation for GoKit, for Goji. If you work in Java, there are for Spring, Sleuth. If you work in PHP, for Symfony, right? Or JavaScript, there are instrumentation for Express. For popular frameworks, of course, there are instrumentation. So you don't need to do anything. You just create your objects and just plug the instrument, and everything will feel the same. But as I said, if you have custom code, if you have custom frameworks, you have to develop your own instrumentation. It's not hard, though. And as I said, instrumentation can be delegated to common frameworks. So if you have your custom framework at your company for gRPC calls, or for RPC calls, sorry, you just need to instrument that. And then everything else will feel the same while doing development. Now that I talk about distributed tracing, I want to talk about a specific distributed tracing tool, so you have a better overview on what it is. Introducing Apache Zipkin. Zipkin is a distributed tracing tool. It's based on B3. B3 was a former distributed tracing tool built at Twitter in 2010 or something like that. It's inspired on Google Dapper, which is a paper that Google published in 2010. In Google Dapper, Google explains what were the challenges and what were the approaches for solution they had for distributed tracing while they were moving to a distributed system architecture. It was open sourced by Twitter in 2012, and this year just joined Apache Foundation. One of the benefits of Apache Zipkin is that it has a mature trace model emerged from users' need. We are not vendors. We are just an open source community, mainly driven by volunteers. We are not a vendor. And it's used by large companies like Netflix, SoundCloud, and Yelp, but also small ones. It's for different sizes of companies. The problem is the same, right? A different scale, but the same problem. And the one that I like the most is that it has a very strong community. You can look at our Twitter, Zipkin project, or you can jump into Gither if you have any question. So, Zipkin architecture. Well, the architecture is pretty simple. You have a service which is instrumented. Instrumented means that it's ready to emit signals, metrics, tracing, right? Then you send it to the collector through a transport. You can send it to HTTP. If you have a big load, you can send it to Kafka, for example, or gRPC, whatever suits you, whatever you have experience in. Then there is a collector. That collector is receiving all the spans, aggregating them in the trace view that we saw. You have a storage layer that persists all this data in a database. The database can be Cassandra, Elasticsearch, MySQL. It can even be in memory. It's up to your needs. Oh, what happened? Okay. And then you have an API on top of the storage for retrieving the data and serving to a UI, right? How the UI looks like? Well, this is the main the main page of Zipkin. You can see all the traces in the list. And you can filter your traces depending on your interest. Are you interested on a specific service? Are you interested on a specific span name? Well, span names can match to, let's say, the root if it's a server span, or the HTTP method if you are doing an HTTP request. It's up to you. And then once you choose one, you will end up in this tree graph, which again has all these benefits of distributed tracing: request scope, it shows causality, clarify interactions, concurrency mute. And yeah, you will see how much time each operation took in which service, right? You can enrich this data with tags and logs. As you can see, you can say what was the host name, what was the request ID, because, for example, we at Typhon, what we do is that if we see evidence of error here, we jump into the logs with the request ID, or the other way around, we have everything connected. I know some companies that have direct link from the trace into the log, so it's up to you. You can put the host name and whatever you feel like will enrich your trace to understand better what happened. You can have also errors. Errors are marked in red, so they are very expressive. And you can see here, for example, how the error was propagated from the video service to the media API, and from the media API to the API proxy, right? Also, what I said, it's request scope, but not limited to the request lifetime, because if you have a synchronous operation, let's say you have a tracking service that does an operation after every request of tracking, which is expensive, that's why you do after you come back to the user. You can see all these asynchronous operation in the same trace, so you can understand what happens. This was very useful for us when, for example, we started doing GDPR. A user request saying delete my account, and that ended up in different messages sent to different services, and they processing that messages asynchronously. You could see what went wrong, right? And finally, you have a dependency graph. And this dependency graph helps you to understand how the services are, how they work together, how they interact, right? And in your mind, what you could be saying is that, yeah, but this is ridiculous, right? You have 4 services, do you need that? Well, you will appreciate when you have such services, right? So, thank you.